Welcome back. In this lesson, we are going to take a look at some features of matrices that end up being important in other theorems and in developing some of the theory behind matrices. So there are lots of ideas here, lots of big ideas. However, we're just going to get into some of the semantics and terminology behind matrices. So there are two types of things when we're dealing with vector spaces. So a vector space is, without getting too into detail with vector spaces, a vector space, you'll see this phrase a lot, and for matrices, this just means that the sum and any linear combination of vectors produces another vector. Any linear combination of vectors produces another vector. Now, what we ultimately mean by this is that whenever we scale vectors, we get new vectors. When we add vectors, we get new vectors. So without getting too technical into the details of vector spaces, we are dealing with this on a regular basis. Vector spaces also apply to, believe it or not, things that we don't think about as vectors, like functions. A set of functions could represent a vector space, and there are certain properties and features of them that has to do with what happens when we scale them and add them together. Now, with that being put aside, there are a couple of features of matrices that become helpful. One is called the row space, and the row space of a matrix A is the subspace spanned by the row vectors of A. So what are the row vectors? Well, there are two of them. There's the 1, 1, 1 vector and the 1, 0, 2 vector. Now for a moment, let me just write these as vertical vectors because it's sometimes more convenient to think about them this way. And what do these span? Well, these are linearly independent. So these are linearly independent. We know that because there are two vectors and we see that these do not lie along the same line. 1, 1, 1 does not have a 0 component, and there's no way to scale 1, 0, 2 to get a 1 component in the y. So these guys, they span a vector, or they span a plane. 1, 0, 2 would be somewhere right in here, and then 1, 1, 1 would be 1 this way, 1 this way, and then 1 up. So it would be kind of like a vector pointing straight up like that. And if you were to overlay a plane onto this, then the plane would be the space that we can span with this. So the way we would often write this is that the span of vectors 1, 1, 1 and 1, 0, 2 is any linear combination of them, C1 times 1, 1, 1 plus C2 times 1, 0, 2. What this really means is that this is any vector on a plane, or any point on the corresponding plane. So the row space is we would say the subspace spanned by it is the set of all vectors that you can generate by this linear combination, where C1 and C2 are any real numbers, including the possibility of negatives, 0, fractions, decimals, etc. Now the column space of a matrix is the subspace spanned by the column vectors of A. So if I look at the column vectors, which are 1, 1, 1, 0, and 1, 2, I see that it's impossible for those three vectors to be linearly independent because there are three vectors in 2 dimensions, and if two vectors are such that they are not collinear, so 1, 0 points here, 1, 1 points there, then I could get to any point I want, say here for instance, by taking the right scalar multiple of the 1, 0 vector and then putting tip to tail the right multiple of this vector here. I can arrive at that point. So one of these is redundant. How do I figure out what subset of these is linearly independent? Well, we know that you have linear independence if there exist constants that are not all 0 such that I can take these vectors tip to tail and arrive back at the 0 vector. So if vectors are linearly dependent, that means two vectors could take me to some point in space, but if they're linearly dependent, that means scaling the third vector can take me back to the origin. And so that means that really I could have taken this green vector to get to that point anyway without having the other two vectors, or I could get to this point with just those two vectors without having the third. So if I solve this system here, 1, 0, 1, 2, and 0, 0 is the augmented portion, what I should find is that I will get 1, 1, let's see, this will be 0, 0 if I perform Gaussian elimination on this, and this will become 0, 0, 1. This should be the actual answer here. I made a little computational mistake, but now that this is in the most reduced form that I can find, I see that there are going to be infinitely many solutions where C1, C2, and C3 are such that C1 is negative 2C3 and C2 is equal to 1C3. So I see that there are infinitely many choices, infinitely many ways in which this could be done. But what that ultimately tells me is that that these are linearly dependent vectors, because it is possible to have C1, C2, C3 not all 0 and get back to the origin in this fashion. The other thing that I should note is that if I look at these three columns here and I double the first column, the 1, 0 vector, I get 2, 0. And then if I subtract away the 0, 1 vector, 2, 0 minus 0, 1 will give me 2, negative 1. So if I take 2 times 1, 0 minus 1 times 0, 1, observe that we get exactly the third vector, 2, negative 1. You might say, but that's not the original set of vectors we were dealing with. The original set of vectors are 1, 1, 1, 0, and 1, 2. But look at this. If I take 2 times 1, 1 minus 1 times 1, 0, guess what that gives me? Well, that's going to be 2, 1 minus 1, 0 is equal, or 2, 2 minus 1, 0 is equal to 1, 2. And so that you see the same scalars here apply over here as well. And so that just tells me that the third vector can be generated out of the first two vectors, and therefore the column space of these three vectors is just the space spanned by the first two vectors in that set. The other way to judge this, in other words, which vectors form a linearly independent set, is to look at each row. So look at row 1. The first one appears in column 1. That means column 1 is going to be kept as part of the linearly independent set. Look in row 2. The first non-zero value that I see is in column 2, and so that tells me that 1, 1 and 1, 0, that's a shortcut way to tell me that those two vectors basically span all the same space that all three of these span together. And with that said, I'll make this conclusion. We'll say that 1, 1 and 1, 0 is a linearly independent set. So the span, the column space of A, which we often denote column space of A, that's is the subspace spanned by the column vectors of A. Well, that means the space that I can span is anything along the plane formed by these two vectors being put tip to tail. So grab the linearly independent vectors within that set and say, okay, anywhere, any tip to tail combination of these two vectors is where I can go. Now, because this will allow you to travel anywhere in 2 dimensions, basically the space spanned is all of R2. It's all of this, infinitely in all directions. So one interesting thing to note is, notice that there were 2 linearly independent rows in the row space, and there are 2 linearly independent columns in the column space. I wonder if there's a relationship there. Okay, now let's define the rank of a matrix. The rank of a matrix A is the dimension of the column space, or of the row space. So what do we mean by dimension? By dimension of the column/row space, we mean the number of linearly independent columns/rows. Notice that both should be the same. Here we have two linearly independent vectors in the column space. Here we have two linearly independent vectors in the row space. So the dimension of, or rather the rank of matrix A from above, the rank of A is going to equal 2, since again there are two linearly independent vectors in the row space and two linearly independent vectors in the column space. So to determine rank, we have to determine how many linearly independent columns/rows the matrix has. Well, let's look at this guy. So we don't need to look at both row space and column space. But notice that here we have three columns, right? 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. Now, by the way, the 0 vector is never part of a linearly independent set. Why not? Because I could always scale both of the other vectors by 0, add them together tip to tail, and I will produce the 0 vector. So notice that these two, however, 1, 0, 0, 0, and 0, 0, 1, 0, these are not multiples of one another. Therefore, these are both linearly independent within that matrix. So again, one thing you could do is just say, is there a constant C1, C2, C3 that will give me the 0 vector? So C1 times 1, 0, 0, 0, plus C2 times 0, 0, 1, 0, plus a C3 times 0, 0, 0, 0, that will give me the 0 vector. And if I solve that using Gaussian elimination, and I do the reduced row echelon form on that, then not surprisingly, we actually get the exact same vectors. There's not any row reduction that can happen here, since there's no elements. There's no non-zero elements that could cancel out other non-zero elements. And so what this tells me is, again, if I look at the first row, I see a 1 in the first column. That means that the first vector is part of the linearly independent set. Go to the second row. In the second row, I see that there's a 1 in the second column. That means the second column vector is part of that linearly independent set. But once I go into rows 3 and 4, I see zeros all the way across. And so that tells me that there are no other linearly independent columns in that matrix. So I could say that the rank of A is equal to 2. The column space of A is any linear combination of these two vectors. So anywhere that I could travel to with these two vectors is exactly what we mean by column space, which this is a 4-dimensional vector, but you can kind of imagine that this allows me to travel in the x and z directions only. So if we could visualize a 4th dimension, then this would be only traveling along the x and z axes. And that's a plane that we would form in 4 dimensions with only 2 vectors. Now the row space of A should also just consist of 2 vectors. Look at my rows, 1, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0. So the second and fourth rows are both 0 vectors, so those cannot possibly be part of a linearly independent set. However, 1, 0, 0, and 0, 1, 0, those are linearly independent because I cannot scale the 1, 0, 0 vector to get the 0, 1, 0 vector. So the row space of A is also any linear combination, any different linear combination of 1, 0, 0 and 0, 1, 0, which is pretty useful. And we see again that both of these have 2 linearly independent vectors. So whether you look at the row space or column space, you can get the same information from it. So we described that it's helpful to use this reduced row echelon form to determine the columns that are linearly independent. We can move on to one more definition here. It's called null space, and a null space of a matrix A is a set of all vectors x such that AX equals 0. So let's think about what this means. We are looking for the set of all vectors in here, x, that once they get multiplied by the A matrix, that what happens to them is they get mapped to the 0 vector. So basically we're looking for the set of all vectors that are characteristic of this matrix, that when they get transformed, they get shrunken down, they get scaled down by a factor of 0. So to find that, and finding it is, again, just using some reduced row echelon form kind of concepts, I'm asking for, okay, 1, 3, 5, 4 times what vector gives me the 0 vector. And so I can build my Gaussian matrix and perform reduced row echelon form on that. And so I will get 1, 0, 0, 0, 1, 0. And so what this means is that x equals 0, y equals 0. That is the only vector that you can multiply by this matrix A and end up with the 0 vector. Well, but that itself is the 0 vector. So only xy equals 0, 0 maps to 0, 0 when multiplied by A. And that's called the trivial solution. Oftentimes, whenever you have something of the form ax equals 0, whether it's consisting of vectors or scalars, like 3x equals 0, the only value of x that will satisfy that linear equation is x equals 0. And so in vector land, that vector, 0 vector is always going to be one that satisfies this equation. Now with matrices, there could be other vectors as well. Now what we would say here is the null space. The null space is the set of all vectors x such that ax equals 0. And so the null space of A, often written as null A, null means 0, that's an easy way to remember this, is just the set of vectors 0, 0. Now if I asked you what is the dimension of the null space of A, that would ask how many linearly independent vectors does the null space of A have? Well, it has 0 linearly independent vectors because the 0, 0 vector cannot get you anywhere. So it is a trivial vector, and so we would say that the dimension of that null space is equal to 0. Okay, let's look at one where perhaps there's going to be more than just the 0 vector. Here we're saying what's the null space of A times x, 1, 3, 2, 6, times xy. What xy vectors will get transformed and produce the 0 vector? So I can solve that system of equations to determine that. And not surprisingly, there's going to be infinitely many solutions, which will be 1, 3, 0, 0, 0, 0. The second row is not a very useful row, but the first one tells me that x plus 3y equals 0, which means that any vector where x is equal to the negative of 3y will be such a vector that gets mapped to 0. So here I see that y is free, so I'll let y equal some constant. And then my null space of A will be the set of all vectors of the form, well, let's see, if x is going to be negative 3y, so that means if y is c, this will be negative 3c and c. And one other thing that I'm going to do here is I'm just going to factor out that c and write it as this. And the reason I'm going to do that is because now I can see that the null space of A consists of any multiples of the negative 3, 1 vector. Any multiple of the negative 3, 1 vector. So as just a little quick check, we know that in the null space of A we would expect the vector, for example, negative 6 and 2. So that would be for where c is equal to 2. And so what I should be able to find out is that if I take this vector And this vector, remember, is just -6 units this way and 2 units up, so it looks a bit like that. And now if I take that vector and I transform it by the A matrix, I'll get -6 times 1, 2, plus 2 times 3, 6, which is -6, -12, plus 6, 12, which equals precisely the 0, 0 vector. So it is the case that this vector got transformed and is now just the 0 vector. There are a lot of theoretical applications of this. For now, it's just important to be familiar with these concepts. Now let's define the nullity of A as the dimension of the null space of A. Okay, so we've already kind of described the dimension of the null space of A as the number of linearly independent vectors inside of that. Now here, the dimension of our null space for this situation, the dimension of the null space of A is going to equal 1 because there's only one vector inside of there that's not the 0 vector. And another way we could write this is we could write this as the, oops, I should use 2 L's here. We could describe this as the nullity of A. So rather than to have to say the dimension of the null space of A, the null space of A is actually a set of vectors. The nullity of A is the number of vectors inside of the null space of A. Okay, so consider again this vector. What are the rank and nullity of A? So the rank of this guy we haven't determined. The nullity of A, we just found out that there's one vector inside of there. And now we should also look at the column space of A. So that's going to be what's going to determine the rank. The rank is going to be the number of linearly independent vectors in the column space of A. So I'm going to ask myself, are these two vectors linearly independent? You may already see that they're not. They're just multiples of one another. Can I find non-zero constants such that this equation is satisfied? 1, 2, 3, 6, 0, 0. And if I perform reduced row echelon form on that guy, I am going to get 1, 3, 0, 0, 0, 0. And so if I go through that process of determining, going row by row, in the first row, leaving 1 here tells me that the first vector is linearly independent, or part of the set of linearly independent vectors. I go into the second row, there's no leading 1 in there, which tells me that the only vector that belongs in the linearly independent set is the vector 1, 2. And you can see that 1, 2, and 3, 6 are multiples of one another. So the column space of A is any multiple of the 1, 2 vector. Well, that means that the rank of A is the number of linearly independent vectors in the column space of A, which is only 1. So notice that the nullity of A is 1, the rank of A is 1, and something somewhat magical happens here. If you add these together, the nullity of A, or the rank of A plus the nullity of A, notice that A is a 2 by 2 matrix. Now, without further proof, but just kind of by observation of how this is going to work, if A is an m by n matrix, it doesn't have to be square, but the rank A plus the nullity of A will equal, in fact, n. So in this case, where we have a 3 by 3 matrix, we should see that the null space of A and the column space of A, when we add their dimensions together, we should end up getting 3. So as the null space of A, and by now we're just looking for what vector, x, y, z, produces the 0, 0 vector when multiplied by the A matrix. And for this guy, we are going to get, so this is going to be for the null space of A. And sometimes you'll see it as the MUL of A. It doesn't really matter which way you write it. And so what we should get here is 1, 0, negative 1/4, and 0. And here we should get 0, 1, 3/4, and 0. And here we should get 0, 0, 0, 0. So once again, we see that by inspection, if we look in the first row, we're finding the null space of A. So in this case, we are looking for these x, y, and z. This is x, y, z. And we see that z is free, so let z equal c. And then x is going to equal 1/4 of c. Y is going to equal -3/4 of c. And z is going to be free. And so that we see that the null space of A is any multiple, is the set of all vectors that map to the 0 vector, and it's going to be any multiple of the 1/4, -3/4, 1 vector. Any multiple of that you can try. You can even try 1/4, -3/4, 1, multiply it by the A matrix, see that it gets mapped to the 0 vector. So then we could say that the nullity of A, which is how many vectors are inside of this set, well, that's only going to be one linearly independent vector. And now we can produce the column space of A, and the column space of A is just going to be the set of linearly independent vectors. Well, guess what? We are actually solving the same system. That is there any multiple of the 1, 2, 3 plus any multiple of the 3, 6, 1 plus some other non-zero multiple of 2, 4, 0, such that we end up with the 0, 0, 0 vector. So in this case, notice that we're hunting for, which vectors are linearly independent here, and if we set this up, well, we're going to get the exact same result, 1, 0, -1/4, 0, 0, 0, 3/4, 0, and the third row will all be zeros. So the difference here is we're just looking for which columns are linearly independent. So if I look in the first row, I see that the first column vector belongs to that linearly independent set. In the second row, I see I forgot my 1 here. My 1 goes there. I see a 1 in the second column, so that means this is part of the linearly independent set. The third row doesn't have a leading 1, so I would say that the column space of A is any linear combination of the 1, 2, 3 vector plus any multiple of the 3, 6, 1 vector. So basically the column space of A is anywhere along the plane that these two vectors form. And so now we could say that the rank of A, we see that there are 2 linearly independent vectors in the column space of A. So this is 2. And notice that if we take the nullity of A plus the rank of A, we get 1 plus 2, which is 3, and that is exactly equal to n from our 3x3 matrix. And that's an introduction to these concepts which you may see further down the road.